Welcome to Lesson 5C, Emission Factors. By way of introduction, I first want to make a note of how to spell emission rates and emission and emitted. These words have one M and two T's. Or two S's. So make sure you spell them right. So we would write emission and we would write emitted this way. The goal is to learn how to estimate the amount or rate of an air pollutant generated by some process. So we'll talk about a bunch of different processes, and I want to mention some notation first before we move on. We'll use S sub j and M dot j as to be the same thing. This is called the source strength or also the generation rate, and it's the source strength of generation of some species J. And keep in mind that sometimes we'll drop the J subscript, especially when we're typically only talking about one type of air pollutant or one species. So keep that in mind. I always like to give the dimensions of these things, so I'll use capital S. The dimensions are mass per time. It's a rate, a mass rate of generation, and then capital SJ bracket, meaning the units of, typically kilogram per day or gram per hour, milligram per second, etc. Now, sometimes we divide by area, so we use a little sj equal capital SJ over A. This would be called the source strength per unit area. An example would be the rate of evaporation of a VOC. In that case, we really don't care how much VOC there is. What you care about is the surface area through which it's evaporating. So that would give you that rate. Again, in keeping with my usual dimensions and units, which I like to do, little sj would have the dimensions of mass per length squared and time. And the typical units might be a milligram per meter squared second, gram per meter squared hour, etc. We're going to talk about emission factors, and these are kind of a back of the envelope or quick and dirty way to estimate the source strength. So we estimate SJ or little sj. So I want to talk about emission factors. So let's define emission factors. Here's the definition in that red box there. EF, we'll call it EF, emission factor, is the mass or sometimes the rate of mass of contaminant emitted divided by some appropriate denominator. So this will be either M pollutant or M dot pollutant. And the denominator depends on the application and the particular type of pollutant source. So just some notes here. Typical units are kilogram per megagram. A megagram is 10 to the 6th gram or 10 to the 3 kilograms. So keep that in mind when you're doing some problems. So when you'll often find these listed in kilogram per megagram because you're creating some product in a process and you do a lot of it, like you're doing some kind of iron ore smelting or copper smelting or something like that. So there's megagrams of product and then only kilograms of air pollution. But it can have any other units, lots of units, that denominator. If you're talking about cigarettes, milligram per cigarette, or kilogram per meter squared for evaporation, kilogram per mile for auto emissions. When we talk about tunnel ventilation, we use that in my ME 405 class. EPA publishes these EFs in a document that was long ago when they first did it, was called AP42. So sometimes you'll hear people talk about AP42 emission factors. There's also an EI, which is an alternate name. This is the website where they have them, and CHIEF means clearinghouse for inventories and emission factors. Keep in mind that these are ballpark, back of the envelope calculations, typically only good to about 1 or 2 significant digits really. But in this course, we will always give our answer in 3 significant digits, especially on quizzes and stuff. So you don't want to round off too much, but keep in mind that these are really just ballpark estimates. The EFs are usually listed with no air pollution control system, APCS, but sometimes they're listed with an APCS. So you got to be careful. When there's no APCS, it's called uncontrolled emissions. Now there's a link on the website to some appendices in my indoor air quality textbook. And these appendices, A2 to A7 of the Heinsohn and Cimbala textbook, even if you don't have that book, I have these appendices in PDF format on the links and references link of the website. So let me just show you that quickly. Up here right before Module 1 is the links and references that are useful to this course. And so if you go all the way to the bottom, emission factor tables from Heinsohn and Cimbala book, and you can go down and see all these appendices for various emission factors. And here's the EF in kilogram particles, in this case, per megagram of raw material. So aluminum production, there's some in different furnaces. So if you have a crucible furnace that's smelting aluminum and you're looking at secondary aluminum, you would have a 0.95 EF, which means 0.95 kilograms of particles are generated by this process for every megagram of raw material, being aluminum, that's being used in the process. And you could scroll down and find this. The easiest way to do this is to do a Control F so that you can type in something to search for. And I'll show you an example of that in a minute. A quick comment here is that you want to always use these appendices unless I tell you otherwise. So for all your quizzes, homeworks, etc., use these. So let's talk a little bit about air pollution control systems. An air pollution control system, or APCS, is some kind of cleaner that removes some of the air pollutant. We never can get rid of all of it, but we measure by the removal efficiency. Before I draw the schematic, I just wanted to mention that we are dropping the J subscript here. So CJ is, we're just going to call that C, M dot generated, comma J, we'll just call that M dot G for generated, etc. So here's the schematic. We have some process, and then that has an M dot G for generated that comes out of it. This is what we're going to get from the EF, typically, the emission factor. You go through an air pollution control system with some cleaner removal efficiency, eta, and then you have a discharged M dot D that goes up into the stack. Stack is just another name for a smokestack or a chimney, and that goes into a plume into the air. We'll talk about these plumes later on. And so that's how much gets discharged into the atmosphere. And I can write the inlet to this air pollution control system, dropping the J subscript, would be C in, mass concentration in, and C out. For any air pollution control system, we have that C out is equal to C in times 1 minus eta. And eta is a removal efficiency. And so this is true for any air pollution control system. Here, we're talking about in terms of M dot, you can write the same thing. So here, we can write M dot D is equal to 1 minus eta M dot G. So we're discharging 1 minus eta times what we generate. So this is in terms of a rate. We can also write it in terms of the actual mass if we're not dealing with rates, but mass itself. So this would just be MD equal 1 minus eta mg. So take your pick, whichever one you use. Now be careful of the 1 minus eta. For example, if eta is 90%, it's 90% removal. So what that means is that only 10% of the original m dot g is discharged. So you take 100% minus 90, or 1 minus eta would be 1 minus 0.9, would be 0.1 or 10%. So 90% removal means that 10% goes through. And so that's one of the biggest mistakes. I've been teaching this for many years, and students will sometimes just plug in eta like in efficiency, say, oh, if I'm generating 100 kilogram per second and I have a 90% efficiency, then I'm discharging 90%, 90 kilogram per second. Well, that's not true. It's 10%, 1 minus eta. So be careful with that. So let me do an example. Here's a steel mill with an open hearth furnace. And you look for the wording here as you're doing quizzes or homeworks or a final exam. The open hearth furnace, which does melting and refining. The furnace refines 8 tons of steel per hour on average. We want to estimate the uncontrolled. What uncontrolled simply means that there's no APCS, which is what the EF tables generally do. So first we look up the EF of particle emissions in an open hearth furnace. And here's a screenshot of that, but I want to just quickly show you how we get that. So I'm here in the appendices of the textbook that I mentioned, my indoor air quality textbook, and I do a Control F. I don't know if this works on a Mac, but on my PC, it's a Control F, which means find. And I can type in, for example, open hearth, and there I find it right away. So open hearth furnaces, kilogram per megagram of steel melting and refining. 10.55 is the EF, and then you scroll up to see what units we're talking about. Kilogram particles per megagram of raw material, which is what I copied here as a screenshot. And so get comfortable with using these tables. You can also look these up on the internet, but again, use these tables unless I tell you differently. So this is the process we're talking about based on the problem statement. So here's my EF. And now we need to come up with some equations. So this is a little bit tricky. You just have to come up with your own equations, typically based on the units. So what I usually do is just write the EF 10.55. This is kilograms generated per megagram of steel that's produced, and we can make our equation based on the units. So this is the equation I come up with. I'm going to say m dot g, the rate of mass of pollutant, in this case, these little particles that are generated, is, well, it's going to depend, of course, on how much you're producing. So if I produce 10 tons instead of 8 tons, I'll certainly have more emission. That's going to be in the numerator. 8 ton per hour that's produced times the EF, which is 10.55 kilogram per megagram. And then the rest is just unit conversions. In all my courses, I preach to use unity conversion factors, which are all equal to 1. This first one is equal to 1. This is equal to 1. This is equal to 1. So you can multiply these equations by any unity conversion factor you want. So when I plug all this in, you can see that all the units will cancel except kilogram per hour, and I get 76.55 kilogram per hour. So I would write m dot g, and these are of particles, because that's what the EF is talking about, particulate matter that's coming out, to 3 significant digits, even though we really can't justify that many digits, but that's what I'll give my answer to, 76.6 kilogram per hour. Now let's do another example of this problem. If we have an APCS with an eta of 85%, how would we calculate the discharge? So if there's no APCS, then this m dot g would equal m dot d. So we'd be done. But the discharged is, from our equation previously, m dot g times 1 minus eta. So using our calculation from up here, we end up with 76.55 kilogram per hour. 1 minus, convert 85% to 0.85, and I get 11.48 kilogram per hour. So I round that to 11.5. Do not do this, where, again, I've seen many students do this. This is one of the biggest mistakes. Just plug in the eta. So you take your 76.55 from up here and multiply by the eta, 0.85, and get 65.1 kilogram per hour. That is wrong. That tells you how much of the pollutant was collected by the APCS, not how much was discharged. So don't make that mistake. Let me do another quick example. Here's also steel, but this is a different kind of furnace. So we're producing 820 megagram of finished sintered steel per day using a basic oxygen furnace. So you can read through the rest of this. In this case, the measurements of the stack exhaust show that we're putting out 125 kilogram of particulate matter per day, and that's what we're emitting. So we want to calculate the overall removal efficiency of the APCS as a percentage. So first thing is to look up the EF, and I'm not going to show you that. Do that on your own. Make sure you can Control F and look up some of these keywords and find it. It was 14.25 kilogram per megagram. Here's the useful equations that I had before. And so all we have to do here is, first I'm going to do the generated, which means without air pollution control system, or before the air pollution control system. M dot G, again, let's make an equation using the EF. So I get m dot g of the particles. This is the generated mass flow rate of the air pollutant. And these are particles, turns out to be 11,685 kilogram per day. I'm keeping lots of digits and just round off at the end. And then the actual emission, this would be after going through the APCS. So we have measured that. That was given in the problem statement. M dot D in this case was given as 125 kilogram per day. That was given up here. And then we need to calculate eta. So now let's solve for eta, and we use this equation, one of these up here. The appropriate one is in terms of mass flow rates. M dot D is m dot G times 1 minus eta, which we can solve for eta and plug in the numbers. And I get 0.9893. So I would write my answer to 3 significant digits as a percentage, just multiply by 100. So 98.9% would be my final answer. Again, to 3 significant digits. I'm going to talk a little bit about how to estimate emission rates. Sometimes this is very easy And the first example here is for VOCs from paint, varnish, etc. So typical paint, this we're talking about oil-based, not water-based, because water, the only thing that comes out is water, so that's not harmful. But for oil-based paints, you typically have approximately 50% solvent, like toluene, for example, some kind of VOC, and then the rest of it is pigments and other stuff that make the paint. And so the point here is that all of the VOC evaporates. I can convince you of that, hopefully, because say you take a can of paint, and all of you have painted walls or whatever, so you take a can of paint, you open it up and you start painting, and so you put a lot of it on the walls. The rest is kind of just evaporated, even if you use up the whole can and then just let it sit and dry out. All of the VOC either evaporates eventually from the wall, it may take a whole day or so, or from the can, that may take a couple days. But all of this, which about 50% of this solvent, goes into the air as air pollution. And so all of it is emitted. Since it evaporates, it's emitted. There's no air pollution control system, since this just goes out the window, for example. Now, there's an exception to that if you have a paint booth in an industrial environment, and then they try to collect some of the VOC before they send it up. So the calculations here are trivial. For example, if I have 100 kilogram of paint and I'm painting my walls, I can say, well, approximately half of that, or 50 kilogram, is emitted. And these approximations are, by the way, by mass, not by volume, so by mass. So if you look up the EF, again, you can do this, look up paint or varnish, etc., and you will see this is in the appendix that I showed you, in appendix 8.3. You'll find that the EF for oil-based paint, and I said 50%, it's actually 560 kilogram per megagram, which turns out to be 56%. But the 50% is a good ballpark number. So this is a EF that EPA puts out. And using our example of 100 kilograms of paint used, M.G would equal that 100 kilograms times the EF, which is 560 kilogram per megagram generated and emitted in this case, since there's no APCS, times the conversion is 1 megagram per 1,000 kilograms, and that gives you 56.0 kilogram that's emitted of VOCs.
Sir, shouldn't that be mg, not m.g?
You are right, Boris. My bad. Let's fix that. And I just copied this screenshot from that appendix to show you where I got that from, and you could look that up. So that's a little bit about EF's emission factors.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.
1, 2, 3. That's all there is to it.